Myself Vishesh Mann. Today we are going to learn about linear and circular accelerators. So before hitting the main topic, we should know that what is an accelerator. Actually, an accelerator is a machine that is designed to accelerate the charged particles using electromagnetic field. Here we discuss about two types of accelerators. First one is linear accelerator and second one is circular accelerators. So accelerators are mainly used for two types of experiments. First one is fixed targets experiments and other one is colliding beams experiment. In fixed target experiments, a particle is shot at a fixed target, while in colliding beams, two beams of particles are made to cross each other. Linear accelerators are used for fixed target experiments, while on the other hand, circular accelerators can be used for both types of experiments. Now, linear accelerator. A linear accelerator is also known as LINAC, which is a short form of linear particle accelerators. Here we accelerate charged subatomic particles using oscillating nature of electric potentials along a linear beamline. And design of LINAC depends upon the type of particle we want to accelerate using LINAC. Principle and working. Actually, we will discuss principle and working in two parts. First is radio frequency acceleration. Second one is focusing. So first we will discuss radio frequency acceleration. When a charged particle is put in electromagnetic field, it experiences a force given by Lorentz force formula. Here, E is the electric field, and V is the velocity of the charge, and B is the magnetic field. So, F gives the Lorentz force that a charge experiences when a charge in electromagnetic field. So in RF acceleration, particle traverses a series of accelerating regions driven by applied voltage. And when a particle crosses each region, then particle sees it an accelerating field. So we have to ensure that particle sees the same phase of oscillator cycle each time when particle crosses the accelerating region. Because if it is not the case, then the particle speed may decrease, which is not a favorable condition for us. So as particle speed asymptotically approaches the speed of light, then relativity comes into the picture and applied force increases the energy of the particle but doesn't significantly alter their speed. Here is the block diagram of LINAC. Here is the proton source. You can take electron source or ion source, and here is the target. So in between we have to accelerate the particles using LINAC. This yellow part of the block diagram represents the drift tubes which increase acceleration by managing the magnetic fields, and the dotted lines represent particle beam. So using electromagnetic fields we accelerate the particles in between these gaps. So why do we need focusing? Actually we need focusing to ensure that particles don't escape the accelerator, or you can say don't escape the reference path that is fixed beforehand the experiment. So quadrupole magnets are required to redirect particles moving away from reference path. So we have to use group of magnets to provide overall focusing effect, as quadrupole magnets are focusing in one transverse direction and defocusing in perpendicular direction. Here is the image of quadrupole magnets surrounding the LINAC of Australian synchrotron. Here quadrupole magnets are used to focus the electron beam. So lastly we will discuss applications. Here are some applications listed below of LINAC. First one is LINACs are used to generate X-rays and high energy electrons for medicinal purposes in radiation therapy. They also serve as particle injectors for high energy accelerators. LINACs are also used directly to achieve the high kinetic energy for subatomic particles, and using these high energy subatomic particles we can demonstrate various particle experiments. Here is the historical image. This child is Gordon Isaac, which is the first patient treated for retinoblastoma with linear particle radiation therapy in 1957 in the United States of America. Now we will move on to the circular accelerators. As we will see, in LINACs the path is linear. Here, as the name suggests, the path is circular in nature. So in circular accelerators, particles move in circle until they reach sufficient energy, and the particle track is typically bent into a circle using electromagnets. So the earliest operational circular accelerators were cyclotrons, invented in 1929 by Ernest Lawrence, or you can say early 20th century, at the University of California, Berkeley, which is a quite famous university. Here is the image of Lawrence's original 4.5-inch cyclotron. Now cyclotron. Actually, cyclotron have a pair of hollow D-shaped plates to accelerate the particles and large dipole magnets to bend their path into a circular orbit using their magnetic field. When a particle is injected in the center of the magnet, they starts accelerating towards the D's due to the electric field, and then due to the magnetic field, their path becomes circular, and then again they enter the gap between the D's, which is again, you can say, accelerating in nature. So charged particles are accelerated by applying an electric field across the gap, and force on the particle crossing this gap is given by Lorentz force law, which is the underlying principle of cyclotron. It is a block diagram of cyclotron. Here we inject ions, and due to the electric field they approach the opposite D, and then due to the magnetic field their path becomes circular and they keep accelerating. So at the end, this is the exit door through which particles can exit from the D's of this cyclotron. So using electromagnetic field, we accelerate these particles to higher energies, and then finally we can extract them from this exit door. So working of cyclotron. When a positive ion of charge Q and mass m is emitted from the source, it is accelerated towards the D having a negative potential at that instant of time, because ion is positive, so they accelerate towards the negative potential due to the electromagnetic force, or you can say Coulombic force. Now due to the normal magnetic field, the ion experiences magnetic Lorentz force and moves in circular path, which we already shown to you. Path is circular in nature, or you can say spiral in nature. By the time the ion arrives at the gap between the D's, the polarity of D's get reversed, so that the particles keep accelerating, or particle speed is keep increasing again and again. And the particle once again accelerated and moves into the other D with a greater velocity along a circular path of greater radius. Now the particle moves in spiral path of increasing radius, which we already shown to you. Here is the path is spiral in nature with increasing radius. So when the particle gain too much energy, the particle with high energy is now allowed to hit the target T. You can take any target according to our experiments. So cyclotrons reach an energy limit because of relativistic effects. As we all know that when speed of particle approaching the speed of light, then relativity comes into the picture. So you can say this is a limitation of cyclotron. So we can modify them into synchrocyclotrons or isochronous cyclotrons. Now we will discuss about advantages of linear accelerators. So circular accelerators have many advantages over the linear accelerators, or you can say LINAC. First one is ring topology allows continuous acceleration as the particle can transit indefinitely. And second one is a circular accelerator is smaller than a linear accelerator of comparable power. Actually, second point is about size, or you can say compactness of the accelerator. So circular accelerator size is much smaller than that of linear accelerator of same power. So now here are some references, you can search them in Google, or this is also a book recommended by me, Particle Accelerator Physics by Helmut Widman Springer. This is quite a good book to know about linear accelerators and circular accelerators. So if you want to know more about accelerators, you can search them. Thank you.